Okay, hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engine, no libraries. It's the complete set of code that's necessary to run a game. And we do this for both educational purposes and also just because, hey, it's kind of fun to do this kind of code. If you're the type of person that likes programming, oftentimes it's kind of fun to get down into the guts of things because it can be a lot more rewarding and a lot more interesting to kind of see how things work and also kind of tinker with them. Right now we're doing some work on, we just started yesterday on multi-threading our application. And the reason that we're doing multi-threading, we covered yesterday basically the problem with processors these days is they are out of places to add speed in terms of clock rate. That is just, they hit a kind of a thermodynamic wall somewhere around the 4 gigahertz range. And so now a lot of the speed that you get from modern processors comes in the form of other things, such as wide registers like SIMD, which we did optimizations for a couple weeks back, and things like what we're doing now, which is multi-core, where you can run several different streams of execution in parallel at the same time and leverage that to make your application go faster. So what we're doing is we're showing how to multi-thread some of the stuff in the renderer. And yesterday I gave an overview of what multi-threading was. If you missed that, please check it out because it contains all the fundamental things that we'll be referring to throughout the week as I show different things. And we also, at the end of the day yesterday, showed how to create a thread in Win32. So now what we need to do today is talk about how we will actually use those threads to do something useful for us. And in order to do that, obviously, we need to start talking about how threads communicate with each other and how they know what work to do and that sort of thing. So we're going to do another Blackboard session today, possibly not as long as the previous one, but another Blackboard session today that talks about the sorts of stuff we need to do in order for threads to work together. And then again, we'll pop back over to Win32 and show how we could do some of those things in Win32. And that should set us up for, at least by tomorrow, actually having the threads do some real work for us. Maybe we'll get to that today, but I don't know. Sometimes the Blackboard sessions take a while to really thoroughly explain things, so you know, that tends to eat up a lot of time. But anyway, so here we are on day 123. So let me go ahead and give a little bit of an overview here. I don't know why we are locked in that mode. There we go. All right, now we're out of it. So yeah. All right, so here we are on day 123. And let's talk about like thread synchronization and also, I guess we might want to call it communication. Right? So where we left things yesterday, I showed how easy it was in Win32 to just create more threads. So basically we could create as many threads as we want. That's really not a problem. And it's obviously very easy for us in Win32 to create as many threads as there are processors in the system. We'll show a little later on, a little further down the line, how to query the system to find out how many threads we should create and that sort of thing. But obviously it's very easy for us to just go ahead and create these threads. But where we left it yesterday, it was not clear how those threads actually start doing useful work for us. So we need to think about a couple things. Now, the first thing that I said yesterday that comes into play here was that threads and processes are not the same thing, right? Because remember, we talked about processes, and processes are different memory spaces. So two processes, in order to share work with each other, have to do a lot of special things in order to make that happen. They have to set up some kind of pipe between themselves and the operating system, or explicitly request that the operating system allow them to share certain memory ranges. So stuff has to happen in order for processes to see the work that each other does or to get the data that each other produce, that sort of thing. But threads are not processes. Threads inside a single process all actually run in the same memory space. So what that means, and we showed a little bit of that yesterday actually, but what that means is that our threads can all work on the same data, right? So basically, if we have a bunch of data here, like in the case of the renderer, right, we had our push buffer, which is what we need to operate on, and then we had like our frame buffer, you know, right? And then we had, you know, our bitmaps and stuff. And what that means is these are all laid out already, and they are accessible by our main thread. When we create new threads, those threads can actually all read these just fine. And so if we just pass in, remember when we created the thread, we were able to share global variables with it, and we're also able to pass in one pointer and Win32 at startup. So there's actually plenty of ways we can sort of tell the thread, hey, here's where the data lives, right? So it's actually pretty easy for this thread to get access to all of the information that it needs. So we won't have to do any real work to make sure that each individual thread can see the things that it needs to see, because unlike processes, threads always have access to all of the memory that's in our process. So that's not a problem. But there are two problems that do have to do with threads. Okay, so number one is knowing what work to do. Okay? Because once we have multiple threads of execution, right, it's a nebulous problem. How do they know what they should be doing, right? Implicit in all of the work that we've done in Handmade Hero so far, and if you've never written multi-threading code, implicit in all of the code that you've ever written, is the fact that you've never had to think about who was actually executing the code that you wrote, right? You just wrote all the code line by line and assumed it would be executed in order by one person, right? By one core that would come along and execute it in order. But once we have multiple threads, that's not the case anymore. All of the code that we have written could be executed by anyone at any time. And we have to start thinking about how we would like to tell each thread where it should do its work. Like what are the routines they should run? What are the data they should run them on? We need some way of actually making that work literally, physically in the code so that these threads know what to do, right? And again, it's implicit in everything we've done so far because our code just started at one place and we just kept calling functions, right? And that's how all the work got done. But now we have multiple people, essentially multiple of these places in the code that are running at any given time. We have to fundamentally rethink our model, right, for how code works, because now there isn't just one big long chain of people calling functions and returning and doing loops. There's multiple of these, and we have to have some model for knowing who should do what work when. Okay, so that's one thing. And number two, we need to make sure that people are sort of, how should I say this? It's synchronization, but it's also the concept that different people are doing different work at different times. So we need a notion of when work is done, right? Or visible. Because there's a problem that I'm going to talk about in detail now that happens with multi-threading that you simply don't have to think about when you're doing single threading, and it's very important. Okay. So I'm going to expand on this because number one is pretty, I think, self-explanatory what I said. It's just a logistical problem. And so we can look at how we solve that a little bit later, but hopefully you understand what the problem is. The problem is all the code we've written so far is just about us calling functions. That's not going to cut it when we have multiple threads. We need ways of distributing work out to these other threads. So obviously the easy problem to understand, maybe not super easy necessarily to solve, but you know, it's clear. Number two is a little harder to understand, so now I want to talk about what that is. All right. So currently the way that we do stuff in our code implicit is we'll do stuff like function A, we'll call it, then we'll do function B, right? And we'll call that. And implicit in this is that this will happen before this. So anything in our code that had an order dependency, the only thing we ever have thought about before is, well, we just put it before the thing that depends on it, right? If function B needs to use the results of function A, we know we just need to call function A before we call function B. Done, right? But once we start talking about multi-threading, we start having to ask the question, what if we want these to happen on separate threads, right? And more specifically, just to give an example of why this might be the case, let's say we had something that actually looked more like this, right? Let's say that we had multiple different ways we wanted to invoke function A, right? And then at the end of them all, we have function B, which takes all of these in, right? All of the things that these guys did, they all wire into here eventually, right? So this is the results of it. This A0, A1, and A2, the results of all these, right, whatever they are, all get wired in here. Now, if each one of these functions is very expensive, let's say function A takes, a millisecond to compute. So we may look at this and go, oh, you know what we want to do, right? We would like to be able to have all of these things run concurrently. So I'll put a thread, thread 0 will do the first time, thread 1 will do the second time, thread 2 will do the third time, and then some other thread, and we don't care who that is, maybe it's one of these guys, or maybe it's a fourth thread even, we don't care really, right? will run function B. Okay, so we assume that we have some solution to this problem, right? We've already solved it. We know how we're going to dispatch these things. They get dispatched and whatever. There's another problem, again, that's closely related, which is that we can't actually, whoever's going to run this function B cannot actually run until all of these other things have been completed, right? Until we know that all of these have been completed, we can't run this one. Which means that we have this other problem when we do multi-threading, which is that threads that need to use the work of other threads had better have a way of knowing that those other threads have finished, right? So these are the two things that we kind of need to keep in mind as we expand our code to be thread aware and to work with threads. This is what we will start to be working on. We are starting in a very easy place, which is the renderer, which is a very easy thing to multi-thread because we're just going to do it in sort of buckets. So we won't have to confront some of the harder problems of multi-threading that might occur if you're working with a less partitionable problem, let's say. But we will still have to do the basic work of doing these two things, and so we'll show how to sort of work through that. Now, the problem here becomes a little more complicated. Or I shouldn't say the problem becomes more complicated. What I should say is the way that you have to solve this problem is a little bit complicated. The reason it's a little bit complicated is because when you are dealing with a multiprocessing system, you no longer even have a guarantee about certain basic things that you might have taken for granted. So what I want to do is talk about this sort of fundamental model of how you have to think about how threads work and how they see each other's results with an eye towards how we're going to do this, right? So let's take this very simple example where I've got some functions A, and I've got function B here, and we want to start actually like thinking about how we would actually implement something if this is what's going on. Because really, if you think about it, this is actually a lot like what's going on. If you imagined that function A was like render one tile, right? And function B was blit to the screen, then this is basically what the sort of thing we do have to do with our render, right? We need some way of a bunch of threads coming in and realizing that each of them should be rendering some different tile on the screen, and then at the end we need a final thread to go, oh, okay, everyone's done. Now I can like sort of commit that change out, say like, okay, let's get that out to the screen. We know all the tiles are there. Okay, so what I want to talk about here, we'll talk about sort of the first part of the problem, right? So let's say I have all of these threads, okay? I've got all these threads, and I don't care for a moment about melting my CPU. I just don't care. I'm gonna just full on spin up all of the cores of the CPU, and they are going to just do what's called a busy wait. They're gonna sit in a while loop, just waiting for there to be work for them to do, okay? So we're not trying to be polite citizens here. We will literally just go ahead and melt the CPU. It will never go into a low power state. It'll all be crazy town, okay? So suppose I was to write something like a for I loop, right, that just goes forever. So my threads, you saw how we created threads yesterday. They just start executing like everybody else. So we have some threads here, right? And all we want to do is be able to basically have something occur, right, which basically says if there is work for me to do, right, if work exists for me to do, right, then I do it. That's it. And then if there's work to do, I do it. If there isn't, I just go back to the top of the loop and look again to see if there's work, right? So it's just a full-on busy wait loop, and we want to see if work exists, right? Well, in a thread, right, inside a given thread, having multiple threads is no different than having a single thread in terms of the capabilities that thread has. Our thread is just executing x64 code just like everything else in our program was executing x64 code back when we were only thinking about programming one thread. And so what that means is this operation here, where I have to say, does work exist, right? That operation has to essentially be done in the exact same manner as anything else might be done. It has to be done by looking at memory, pulling things into registers, doing operations on those registers. It has to be done in a way that a CPU can just do. It doesn't magically get any different because there are threads. We have to construct this out of the same primitives. And what I want to show here is that is actually a relatively tricky problem, okay? The reason it is a very tricky problem is, let's say that our solution to this is just to make a pointer, right, out in space somewhere. So we've got some pointer, here it is. And that pointer we will set to 0 if there is nothing to do, or we will set it, if there is something to do, to point off to like the render buffer, right? So the buffer is out here. So all we want to do is we want a thread to come along and see if there is work there. If there is, we want it to pick it up and we want it to do it. Okay, that's all we're trying to do. Very, very straightforward. Doesn't even totally solve the problem we were talking about. All we're trying to do is just that, right? So if we were to write that, right, this code would look something, you know, like if pointer, right, render pointer. Okay? That would work just fine for a single thread. It would loop through, it would just sit there, and as soon as we stuck some work in that pointer, it would come along and it would render what was in the pointer, right? Now, the problem is if we had more than one thread who were sitting in this loop, right? Well, multiple of those people would come, they would see that the pointer was pointing to the work, and they would start doing it, which would mean that more than one thread would start doing the same work, right? And we don't want that to happen, because if we're going to make a good system for distributing work here, one of the basic things we have to do is make sure that no two threads do exactly the same work and, like, you know, waste all of that time, right? We want to make sure that threads are always doing new work. So what we might think of is say, well, okay, if we see that there's a pointer pointing to some work, then what we'll do is right away after we see that, we'll set that pointer equal to 0, so that now no other thread will see the work that we're going to do, right? So we'll essentially do, you know, we'll save the pointer ourselves. So we'll kind of do like work equals pointer, right? Pointer equals 0, and then we'll call, you know, render work. So we'll clear out that pointer as soon as we see it, all right? And this is the part that I want to talk about right here, because while that seems like it would work, it won't actually work. And the reason that it won't actually work is because multi-threading introduces, like I said, a whole another set of subtleties that you don't normally think about when you think about single-threaded code. And the reason is because if you look at this from the perspective of two separate threads that might be sitting in this loop waiting to do whatever work comes there, they would look like this, right? Both of them have an if pointer. Both of them try to save the pointer, work equals pointer. Both of them try to set it to 0, and both of them try to do render, right? Like so. Okay? So the problem here, and I'll just put little braces around there so you can see it. So the problem here is that if one or the other of these blocks happens to execute essentially all by itself, we don't have a problem. If this thread here says if pointer, work equals pointer, pointer equals 0, and manages to get here before this thread ever does anything, we're fine. But what could easily happen, because these two cores are both running at the exact same time and could be executing any of their instructions at the exact same time, is they both could look and say if pointer, right? And before this guy has cleared out the pointer to 0, this guy actually advances inside the if, right? And he goes ahead and takes a copy, and they both overwrite the pointer with 0, but it's too late now, and they both go and do the work, right? So essentially what I hope you will sort of appreciate when I'm illustrating here is that actually, given the primitives that we've worked with so far in C, C actually doesn't really give you any way to even create something where you can guarantee that two threads won't do the same work, right? In fact, I don't even think there is a way to do it in C at all, without going to like C++ or some C++ 11 or something. But as you know, multi-threaded code does actually work, and people ship it all the time. So how is that happening? The reason is because x64 actually provides a number of instructions that help with this, right? So there are basically special instructions that are designed to facilitate the fact that you need to write code that looks this way in order to make multi-threading code function properly. And the way that these special instructions work is they typically put operations into a context where you can guarantee that only one thread will see a particular result and no two threads will actually see that same result. So I'm going to give you a very simple example of that right now. There is a function that the x64, there is a instruction that x64 can do, for example, which is a locked increment. It's called a locked increment. You can access it by using interlocked increment in Win32, which we may or may not use. We probably won't actually use that one, but I'm just going to give it as an example. And what a locked increment is let's suppose that I wanted to, well, actually, you know what? Why would I introduce that one when I have the one that would actually solve the exact problem that I wrote? So let's do this one, locked exchange. Okay. What a locked exchange does is it says, I would like to replace a location in memory with a new value. And I would like to ensure that nobody else will be able to perform the same operation at the same time. Okay? So what it does, if we were to change this here, right? Because you can look at what we're doing here. What we're trying to do is exchange whatever is in pointer with 0. We're trying to put a 0 in and get whatever was in there out. And we want to make sure that we are the only person who can do that, right? We want to make sure that when we do it, nobody else will be observing the value that pointer actually is at that time before we stuff the 0 in there, right? That's what we want to make sure happens. So what the locked exchange does is it says, all right, I can do a locked exchange, right? And I can say the location that I'm trying to exchange is pointer, and the new value that I would like to put in there is 0. This locked exchange will provide me the result, which is whatever was in the location pointed to by pointer, right, at the time, and it will put a 0 in there before anyone else can observe that result. So if some other thread at the exact same time is also executing locked exchange, right? So if we have another thread that's also doing a locked exchange over here, it will guarantee that one or the other of them will actually get pointer, what was in pointer, and replace it with a 0 before the other one gets the value. So the other one will get that 0 swap, right? If that makes sense. So what we can do is we can rewrite this routine we can rewrite it to make it work, right? By saying, okay, instead of doing it that way, what we'll do is we'll say, all right, we have whatever the work pointer is up here. We've got work, right? And what we'll do is we'll say work equals interlocked exchange, right? The pointer and 0. We can then say if work happens to actually be valid, then do the work, right? And what this will guarantee for us is that if work comes back with a valid value, as long as everybody else who was ever trying to observe that value didn't just cold read it, because other people could cold read it. They could do star work, they could just look at the pointer, and they'd see what was ever was in there. But as long as everyone else is also only doing it with an interlocked exchange, we know that only one person will ever be able to actually get back the value, because as soon as they get back the value, it will get overwritten with that 0, right? So that is how multi-threading code works essentially in a nutshell, the synchronization primitives, how they work. They are all based around using special versions of functions that are coded in x64 to ensure that no matter how many cores happen to be banging on this piece of memory at any given time, they will all serialize themselves into a line properly and retire in a particular order that guarantees that no two people will be able to do that same operation. So that's very good. And like I said, there's other ones like interlocked increment, which will take a location, increment whatever the value is in it, and return you whatever the old value was. And it will guarantee that if everyone is doing interlocked increments, you will only ever see, each person will see a unique value in the series, right? So you can kind of produce like an escalating series of integers, for example. Now, the granddaddy of all of these, the big papa, right, is a function called interlocked, well, an instruction, interlocked compare exchange. And I want to mention this one because this is probably the one, if you only learned ever how to program one thread synchronization instruction in x64, this is probably the one you would want to use because it is crazy powerful. Interlocked compare exchange allows you to do essentially the same operation as an interlocked exchange, but it allows you to do it predicated. So in most circumstances where you don't super care about the absolute maximum performance of the interlock point, right? Because these instructions, keep in mind, these instructions are on the order of like 100 cycles or something. I don't even know what they are nowadays, but they're not many, right? But if you were doing tons and tons and tons and tons of these, right? We're not probably going to be doing tons and tons of these. We'll be doing 50 of these or something, or 100 of these, right? We won't be doing that many. So we don't super care how fast the interchange happens to be, because our goal is to do very few. We want to basically partition the work into very large chunks, so we're not spending a ton of time figuring out who's supposed to do the work, right? That's not really where we want to be. But if you are in that situation, then maybe interlock, compare, exchange is not for you. But in circumstances where you have a reasonable number of cycles to spend doing your thread synchronization, interlock, compare, exchange is kind of amazing, because it lets you write basically any old janky, crappy code that you want and still have it work. I know that sounds a bit strange, but it kind of is actually true. Why is it true? Well, the reason it's true is because if you take a look at how this code was working, right, you can sort of start to think about it. I know it's a little bit hard for you to conceive, because if you haven't done a lot of multi-thread coding before, you're not really thinking through all of the possibilities here and whatever, but you can sort of kind of extrapolate that, well, okay, if this is the operation that I had to work with, interlock, exchange, well, basically I'd have to phrase every last little thing that I might want to do as a single swap, right? I have to kind of make this single swap do all of the work. So I have to prepare things so that it all just fits through there. So it's kind of hard for me to figure out, like, oh, if this thread wants to go look for things and decide what it wants to do and then maybe do it, how do I boil all that down to like this single swap? It's a little annoying, I don't know, maybe like complicated work distribution schemes, how am I going to write them, etc. There's a lot of thinking that might go into that, and you might have to do a lot of cleverness to make this happen, right? Interlock, compare, exchange is not that. Interlock, compare, exchange is a thing that lets you be super piggy. You can put on the pig hat. For example, I'll put on the pig hat while we're even talking about it, because it basically enables some pretty piggy behavior and doesn't really make it into too much of a problem, right? So how does this work? Well, what this does is it's essentially the exact same thing I just said. It's the same as the interlock exchange, but what it does is it takes a value that you are expecting to see in pointer, and if that is not the value that is already there, it does not do the exchange, right? So basically what happens is with interlock, compare, exchange, you can essentially write code the same way you've always been writing it. You can do something like, okay, if there's work there, no thread synchronization, I'm just going to look and see if there's work, scan like through the work, figure out the ones I want to do, rearrange some things in my own store, whatever, do a bunch of stuff here. And then when you get to the very end, right, you can then go, okay, if interlock, compare, exchange, right, I'm going to call that ICE, interlock, compare, exchange, because it's a cool acronym. If interlock, compare, exchange, do the actual swap to move out the work, right, and do some stuff. And what this does is it allows you to go, oh, if some other thread actually got there before I did and replaced the value that used to be in work with some other thing now, I'll know, because this won't succeed. The exchange won't go through. And I can actually just not do any of the stuff I was planning to do, right? And let this come back around, right? Because usually, like I said, these are in loops waiting for work, right? Let this come back around and try the whole thing again, right? So what you can actually do with interlock, compare, exchange, if you don't mind being a little bit picky, is you can actually write some pretty crappy thread code, and it actually can work thread safe just by keeping it arranged relatively smartly with interlock, compare, exchange. Whereas if you are using one of the other primitives, that is not the case. You pretty much always have to be sly fox and sly fox it around, right? Because if you don't have it worked out just right, if there's any work that you were doing at all that is sort of counting on being done outside the interlock exchange, but not while the other thread sees it, you will end up with some kind of a bad synchronization problem or crash or anything else. Who knows, depending on what the particular circumstance actually is, right? So that is basically that. for thread synchronization. So what we are going to do is we are going to try to use these to build some way of us having our multiple threads to do the work that they need to do. And there's only one other thing. I want to reserve a fair bit of time to go back there, so I'll spend another 5 minutes now and just briefly mention one other thing since we're on that topic, and that is simply sort of about reads and writes in a multi-threaded context. I want to just sort of preload this. We probably will talk a little bit more in detail about it further down the line. But what you have to understand with threading is that once this sort of concept is on the table, and you know, I've done it once for you here, but we're going to talk about this a lot, and you have to be aware of it. Once we, you know, are multi-threaded, this is always the way you have to think about things. You always have to think about things the way I was thinking about it here, where any thread could be at any point in its execution at any time, right? So you always have to think about what might happen if two threads are trying to do something with the same piece of memory at the same time, right? And what this means is that reads to stuff that is constant are always fine. If I have a bunch of threads that are doing work and they want to read from some database of values that never changes, then I don't have to worry. A read just always works. Writes, on the other hand, right? Anytime two threads might write to the same place, you have a problem. Because if two threads might write to the same place, you have to ask yourself which one of the results did you actually want to happen. Now, if they're both going to write the same result, that's not a problem. Hey, two threads could overwrite the same value with a new value that happens to be the same. That's not a problem, right? But once threads are writing to the same place, you have a problem, and you have a synchronization problem. So that's something you need to keep aware of, because obviously, you know, whoever writes last will be the value that gets stored there. That's an issue, right? But it gets even a little more complicated than that. And that is because once you start talking about threads that are writing to places where other threads might also write, even if they don't really read from them, you may actually have secret places where they do, in fact, read. And the reason for that is because the processor actually thinks about things in terms of cache lines. Okay? Now, we haven't talked very much about cache lines in the past because we haven't really had to. We've talked a lot about the cache, and we say things like the L1 cache and the L2 cache, right? And we talk about these being things where, you know, you go out to the cache and go out to memory. Well, the cache, as it turns out, is the primary place where synchronization happens in the processor. Meaning, when the processor cores think about coordinating things themselves, like, for example, these locked increments and stuff, right? Interlock, compare, exchange, and those sorts of things. Even though those things appear to be operating on 32 or 64-bit values, really, processors, when they're thinking, the cores, when they're thinking about this, are thinking about them in terms of who owns what cache lines, right? And a cache line is some size that's much larger than 64 bits, right? And it depends on the size of the processor, how big the cache line is, but, you know, it could be something like 128 bytes or 256 bytes or 512 bytes, right? There's some number of bytes that comprise a cache line. And what happens during these reads and writes is that processors try to take ownership of lines of particular segments of memory in terms of a cache line boundary, which they then operate on and then commit, right? And what this means is that you, in your code, may think, oh, you know, here's what's happening in my code. I've got this struct, and there's, you know, an int here, an int A, and there's an int B, you know, in the code, and, you know, oh, one of my guys is just reading and writing from this A, and another one of these guys is reading and writing from B, so there's no problem. It's fine. I don't need to do any interlocking. I don't need to do any synchronization. I can just use standard old C and read and write from A and B all I want. That may not actually be true, because depending on the processor and depending on the situation and blah, 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 you may be in a situation where, since you have not told the processor about this, these may be on the same cache line, which means you could get crazy stuff happening, such as, you know, here's core 1, here's core 2, right? Core 1 goes, oh, I'm supposed to read and write from A. So it loads in this cache line into its cache. And here's A, and here's B, right? And we'll say that these are A0, B0. They're the state of this thing at some time. And core 2 happened to be executing some code totally in parallel. It's like, oh, I've got to read and write from B. So it loads this into its cache, right? So it's got, here's our A and here's our B, right? Now they go, oh, you know what? Cool, dude. I just got to modify A. So I execute a piece of code and I end up with A1. So it's like, you know, this is some other version here. I've got A1, A0, B0, right? And B is still B0. Core 2 goes, oh, you know what? Cool, dude. I got this. I'm going to modify B. So now it's B1, right? Later on, when they go to commit these cache lines to memory, right? Again, depending on the architecture and depending on all sorts of other things, they may then go, oh, okay, let's just commit these guys back to memory. They commit them back to memory, right? And what happens is one of these two cache line commits just overwrites the other one, right? Or something equally heinous. So you just end up with A1, B0 or something like this, or you end up with A0, B1, right? So that's bad. And you have to essentially know, again, information about your particular processor or whatever. On x64, my recollection is that this is not something that you have to particularly care about, right? Because in general, I'm pretty sure that it guarantees that writes are always visible to other processors. So as far as I'm aware, and someone on the stream can correct me out if I'm wrong, as far as I'm aware, on x64, you never have to think about weird stuff like this happening, right? Let me think about this before I say that. I feel like that's correct. We'll double check it, but I'm pretty sure that the way the x64 memory coherence works, it's that writes are always visible in a particular order. And so you don't have to actually worry about that particular case happening. I believe. I could be wrong about that, but I believe. It's buried in the Intel System Architecture Manual. I remember reading this very carefully when I first started doing multi-threaded programming, and I believe that unlike other processors, which actually you have to be more careful about this sort of thing, that Intel has a very strong memory ordering model that prevents this actual pattern from ever occurring. It just knows, it's smart enough about those writes that it won't do that particular operation on the cache lines. But again, could be wrong about that. Point being, you have to think about these sorts of things. At the very least, again, even if you weren't going to think about them from the perspective of just, oh, you know, on some processors I may have to think about this because I'll get wrong results, you still want to think about them for another reason altogether, which is that if two cores are starting to have contention for a particular piece of memory, again, that, you know, it's not free. It's not like the processor internally has some magic way of making all these things work out at no cost. It's still, all of the synchronization still has to happen somewhere. So even if you're on an architecture which guarantees that you can do stuff that will not be a problem as far as these kind of writes are concerned, you may still want to be aware of it because you don't want to have two cores constantly pounding on the same cache lines, because that will create synchronization work for the processors where they have to constantly talk to each other to shuttle their results back and forth. And that is, again, not free, typically. So again, just want to bring that up. There's things you have to think about. And so if you can, most of the time, what you will want to do is you will want your cache lines you want to think about things in terms of cache lines, and you will want to try as hard as you can to make sure that the primary work that your cores are doing line up along separate cache line boundaries, so that while your two threads are executing, either A, you're guaranteed correct results on platforms where you have to make sure that that's not the case. You're guaranteed correct results without having to start using a bunch of synchronization primitives like the locked versions, right? Or on an architecture which gives you strong memory ordering and you don't have to worry about getting incorrect results, you still may want to do it because your performance may suffer. If you're sitting there forcing the CPU to constantly talk and say, oh, hey, I got that cache line, here you go. Oh, wait, I need it back. I got to update the value. Oh, wait, you need it back? Okay, great. And they're shuffling it around all the time, right? Not free. So that's something to think about there. We'll be talking more about this because there's things like memory barriers and fences and all these other sorts of things that happen in terms of write coherence. We'll be talking about that sort of stuff a little bit later, probably tomorrow when we get to, when we actually have our routine fleshed out, and we need to talk about how to make sure that it operates correctly. But for now, we'll leave that. All right, so let's flip back here. take off the pig hat because I'm not actually doing anything piggy, right? And let's go ahead and, man, that pig hat is hot. I sweat when that pig hat is on. I guess that's good. You don't want to be piggy, so I guess that's a good penalty for if we ever be piggy in the code to try to convince us not to be so piggy all the time. So, all right, let's open this up here and let's go back to our thread proc we created yesterday. And we got about 15 minutes here, so I want to kind of show how to actually start doing some work with the threads. Very basic, but just try to get it so you can sort of see how that's working, right? So what I'd like to do is I would like to make something, and we'll just make a very simple toy thing right now. I want to make something where we can make 4 threads that each do some work, and they do different work, okay? That's what we want to do. And so what I'd like to do is something where, for example, maybe each of the threads prints out a different string, right, after the fact. So, for example, we do these create threads here, this create thread stuff here. Right now we're passing in a string. I want to make it so I can basically make a little queue where I maybe put some strings in and they'll print out the strings, something like this, right? So what I'm going to do is I'm going to create a little thing that's like thread info here or something like this, just temporarily. We probably want something actually like this eventually, but it's going to be just a little placeholder for now. And all I'm going to do here is I'm going to put in something like a logical thread index, which is basically just a value which says this particular thread is number 0 or number 1 or whatever, right? So that we know what they are. And what I'm going to do is I'm going to say that Win32 thread info, right, is going to get passed in here to the function as that LP parameter. So I can basically, and I can use this in the future to pass anything else that I want to the start of the thread so it kind of knows what's going on, right? So then what I'm going to do is I'm just going to create some of these threads, right? I'm just going to go ahead and make this a loop. I don't know how many threads we want. I guess we said there were 16 cores. Maybe I'll create 15 of them, let's say. So I'll do a thread index equals 0. Thread index is less than 15 rather. And then we'll do thread index plus plus. And then when we're in here, we'll do win32 thread info. We'll make that info struct. And then what we'll do is we'll set the logical thread index. We'll set that equal to whatever number it was in our array. So we're going to create 15 threads. And then what we do, instead of passing 0 here, instead of passing param here, which was this thread started thing, we're actually going to pass an address of that struct. And so as you can see, oops, that's no good. Didn't do that. There we go. As you can see, this will just pass through to here, so we can pick up that thread info. We're just passing this through to this routine, right? So once we do that, we then have a bunch of these guys, and for right now, they're all just going to sleep, right? And so if I run Handmade Hero now, again, nothing in particular really will happen because those threads will just sit there doing absolutely nothing. They're just sleeping. And our Handmade Hero runs as it normally would run, right? No big deal, and I exit. But those threads are being created. So now what I want to do is I want to take these threads and I want them to actually look for some work to do, right? That's what I would like them to do. And I want to make sure that each of them gets the right work to do, right? So what we're going to do here is we're going to have something like, I guess maybe just an array, let's say, something very simple. And what this array will be is it will be like a little mini queue, right? It'll be like a mini queue. So I'm going to do like a work queue entry thing, something like this. And I'm going to have in that work queue entry, I'm going to have a char pointer, which is like the string to print, right? And we can put other work here that we wanted to do, anything like that. And then what I'm going to do is I'm just going to make this work queue entry. I'm going to make some number of these, right? I'm just going to make a bunch of them. I don't know how many I'll make. Maybe I'll make 256 of them. And then I'm going to have an index into them that says, here is the current count of them, right? And so I'm going to do an entry count, like so. Make sense? And this is obviously a value that gets initialized to 0 at start. Okay. So the first question is, what happens if I just start pushing things in here? So let's just write the code with no thought to thread synchronization whatsoever, and we will see what happens, right? So first we're going to start up. And inside each of these threads, what I want to do is I want the thread to basically just go through and do any work that happened to be there, right? And so I guess what I should do first is I should push some things on there. So let me just do like a push string, and I'll put in string 0, right? Something like this, right? 2, 3, 4, 5, right? And what I'll do here is I'm just, again, I'm just going through and putting some in. Maybe we'll do, I'll do 10 of them. So there we go. We've got 10 of those guys. So we've got 10 strings in there. And now what I want to do is I want to make a little function. I want to implement this push string. So what I want to do is make that so it just goes ahead and adds one of these into these entries, right? So I'll just go ahead and say we've got internal void, right? Forget, you know what? I had a value for this, right? Just global, right? Yeah, okay, good. Maybe not. Handmade platform. What was global? Global variable. There it is. Oops. Okay. I don't like to use the word static because it means too many different things. All right. So inside push string, right? Very, very simple. It's taking some string that's going to push on here. All I want it to do is basically say, all right, I've got a work queue entry, right? It's going to be whatever the entries are, entry count plus plus, right? Maybe I'll assert here that the entry count is less than the size of this guy, right? So I don't want it to ever overflow the array for now, or not that we're ever going to push that many on for this test code, but still. And then we're going to have that string to print is going to be equal to the string that gets passed in there, right? So that actually works now. Oops, did that the wrong way. There we go. So that actually works now, and now the strings will get pushed on there, right? But we need to actually pull them off. And so what we need is, we don't really know where to pull these guys off, right? So we kind of need, we have the count of entries, but we don't actually know. We need like a second variable, right? Which is like the last printed entry, or the next entry to print might be the right thing, right? So it's entry 0 right now, and basically as long as this is below this value, we need to print out a thing, right? So in here what we want to do is we want to say, okay, if the next entry to print is less than the entry count, right? Then we want to go ahead and print it. So we want to go ahead and grab it, whatever it is. Well, work queue entry. The entries equals the entries plus the next entry print. I should say to print. Or I should say x. Next entry to do might be the better thing, because in case there was something other than printing in there. So if the next entry to do is less than the total number of counts, I'm going to pull it off, right, and increment this value. And then I'm going to actually do the output debug string for the entry, right? String to print. And while I'm at it, what I'd like to do actually, I think, is I'd like to go ahead and actually build a buffer here that actually has some more information in it, because I'd like to know which thread actually did it. So I'm going to call Windows and say, why don't you prepare this buffer for me, right? Which says like thread, and it gives the number, right, of the thread, and then it does the string that got output, right? So I'm going to actually create a thing here. So we have that logical thread index. Here's the thread info, logical thread index, right? And then I've got that entry string to print. So it's going to form that up, and then it's going to output that buffer to the debug console, right? So there we go. And one thing that, well, I won't even mention that now. It doesn't even matter. So there we go. We'll build that up. Logical thread index. Oops, sorry, that's a pointer. There we go. And we'll get this working, right? And again, we've done no synchronization now, so this code is totally not actually safe. But I wanted to show you the unsafe version first, so that you kind of get a feel for where we're going with each of the changes, right? So off we go. I don't know exactly what is happening there, actually. Let's go ahead and close that out. So let's take a look. So this is pretty weird if you take a look at what actually got printed there, right? I think I may have had a bug in there, because that's even weirder than what I thought it would originally print, which is thread 14 printing all kinds of weird things in that string, which should have pushed them all on. And I feel like that actually shouldn't have printed something so odd. That is very strange, if I do say so myself. Yeah, so that is actually not what I would have expected from the unsafe version. I would have expected, if one thread printed out all of the things, I would have expected it to, duh. Okay, good. I thought I was going crazy there for a second. I forgot that I need to let these guys persist. So you see what was happening there, right? Each of these thread infos, I want these thread infos to persist so these guys can use them, right? But what's happening is I only have one on the stack here, right? So what I actually wanted, I want this, right? Which is, you know, however many threads there are going to be or whatever, right? There's 15. I want to do it this way so that each of these still exists and these guys can continue to reference them, because otherwise they just keep getting wrote. So that was just garbage. That was just me. That was just mental stupidity there. So we got these thread infos, right? So all I need to do is just make sure that they all continue to persist, and then we're fine. So no big deal, but that, yeah. I was going to say, there's definitely a bug in there somewhere, because like that, even though this is not the safe code, it should not be printing out something like that. Okay, so let's give that one more go here after we create all these threads. Let's see. All right. So there we go. Let's see what we actually printed out. All right. So here you can kind of see, and in fact, this is now roughly what I would have expected to see printing out. You can kind of see, you know, the results that we end up getting. Basically, thread 14 printed out sort of the 3 of these guys here. Thread 13 printed out these 2. Thread 5, 2, and 0, and 4 all got the same string at the beginning, right? And thread 1 got string 4 somehow, right? So, I mean, you know, again, I have to check to make sure I don't have any other bugs in here, but this is a totally plausible thing that could have happened even if there are no bugs in this code, right? And it's totally wrong, but this is what happens when you don't take the proper care to have your threads actually synchronize and look at the proper work, right? So, what are all the things that are happening here? In 3 minutes, I'm going to say what they all are, and then tomorrow we will start actually just fixing them all. They're not particularly hard to fix, but you know, we'll get started on it since we're almost out of time. So the first thing is right here, right? So with our next entry to do, I'm going to pull that out into a thing. So I'm going to do like a entry index equals next entry to do plus plus entry index, right? Okay, so the first problem is this line, right, is not interlocked, right? So 2 threads could see the same value at the processor level, right? This is what I was saying before, right? This thing right here where I do the plus plus, we have not told the x64 processor that it needs to worry about other people who may be doing the same thing, right? And so that is obviously going to create a problem. On the same line, we have another problem, which is that the compiler doesn't know that that multiple threads could write this value, right? And what that means is that even after we were to take care of this, right, in theory, and this actually isn't really true because you'll see it automatically does this for us in a way that will be clear in a second, but if the compiler is not made aware of the fact that this value could be getting changed by other threads, it may just optimize this out. It will look at this loop and go, oh, he's the only person who changes, you know, this value or something, so I can just hoist it out or do other things with it and it's fine, right? And the answer is no, it is not fine. I need you to check that value when I tell you to. You can't go moving it around or changing what it actually does. And so there's a C keyword that we need to put in there to make sure that it understands that as well. So that's another thing. That's a problem, right? The other problem that we have is here in pushString. So in pushString, right, this entry count plus plus, we've got another thing here, which is that these writes are not in order, right? So if you take a look at what happens here, you can see what I'm doing. I do the entries plus the entry count, and then I have the string to print that gets set there. So first of all, what you may notice is as soon as this value goes up, right? As soon as entry count gets incremented, one of these threads could look and see it, right? Whenever this processor core decides to put this value out, one of these guys will look and it may see that entry count has gone up and it will start doing this work and loading this in. If that's the case, right, then I had better make sure that string to print is already filled out, because otherwise it's going to go and get garbage, right? This value will be garbage because it hasn't actually been written here. So the other thing that we need to do, the final thing that we need to do, is make sure that the writes to these things happen in order so that by the time it's possible for one of these threads to see that entry count has been incremented, there is no chance that the work that they are going to go and get has not already been flushed out to memory, right? I shouldn't say flushed out to memory. That is not already properly noted in the architecture, however that has to be notated in the particular architecture that we're on, right? So just in this very simple piece of code, and I hope this underscores just how important it is to be careful when you're doing multi-threading, just in this very, very simple piece of code, there are actually 3 totally separate things that are not correct that have to be rectified. And we will sort of talk about them in order. And technically, there really is one more that I'm going to put in here, which is that the same thing that happens with those writes, there's the same problem with the reads, which is that technically, and especially if you're talking about the compiler, again, certain architectures guarantee strong ordering for different things. So this may not actually be a problem on the x64 architecture at the architecture level, but at the compiler level, it may be important. What you have to remember is the compiler is technically free to hoist things like these reads outside above things. What we want to make sure is that it never does things like that. So technically, we may want to also put in things that prevent that from happening. Okay? So yeah, again, this is one of the reasons why you tend to want to write a few very simple primitives like a work queue or things like this, like sort of what we're working towards, in order to facilitate your multi-threading, because once you start talking about threads having to do work with each other, it gets very complicated, and so you want to typically solve that problem once in a coherent way and not have to keep doing it all throughout your code, because you're very liable to make mistakes, and you would rather only make those mistakes once and fix them once rather than having them strewn throughout your code that, in a way that constantly causes you bugs and headaches. All right, so with that, let's go to the Q&A. And let's see. Questions. Is your use of for semicolon semicolon instead of while one a stylistic choice, or is there a benefit drawback that I'm missing? It is actually just to shut up stupid compilers. So for some reason, a lot of compilers, if you do this, will complain at you, right? And what they'll say is conditional expression is constant. It'll be a warning. I probably, I don't actually know if I can do this, minus all. There we go. So let's see, if I turn on the most strict warning level here, which of course I can't do because the Windows headers. Oh, well, you know what? Well, yeah, the Windows headers are problematic, and I'm in that file, I guess. But let me just take a look and see if it has it here. Oh, you know what? I may have disabled it even. Let me see if I get rid of our warning disables. Conditional expression is, yeah. So that's the warning. It's conditional expression is not constant. I disable that warning because it's the stupidest warning. But that's why I tend to prefer this, is because if I'm running code, especially in another code base, like, I'm working on the witness or something, and they don't have that warning disabled, I just try to make sure that I don't introduce any spurious warnings into the code, right? So I'll try to prefer that. That's the only reason. What's the problem with not being interlocked and seeing the same value as your to-do suggests? This one right here. So that's the one that we went over on the Blackboard in detail, right? It's that we want only one thread. We want only one thread to actually see the value, say, 0, right? Because our goal is to do each of these units of work once. And what we see already, right, is that's not happening. Thread 5, 2, and 0 all did the wrong piece of work here, right? Which is not good at all. And yeah, I feel like, again, I feel like there's still some jankiness in here. I gotta see what happens. Let me see what happens if I do only one of these threads. Just want to make sure before I start talking about this that we're all good here. Yeah, so you can see this with one thread, it prints out the numbers 0 to 9 in order, right? So each thing is being done once. If I make 2 threads now, right? We go up here, and they're still doing okay, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And thread 1 did 2 of the units of work. Thread 0 did some other ones, probably because it had time to do those before thread 1 got created or something like this. We'll step up the number one more time. And 0, 1, 2, 3, 4, 5, 6, 7, string 6. So you can see thread 1 actually got string 6, but printed it out later, just to the way these guys ended up happening to go. But again, still all good there. So we're lucking out pretty well as we have this. But again, it's really just luck. It's also helped a little by the fact that there's a string synchronization. This output debug string actually synchronizes because only one person can write to that debug sync at a time, so you kind of have a little bit of synchronization there. But what you can see is once we get up to 4, you can see that we got pwned, right? 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we did one set of the work twice. Both thread 0 and thread 1 both saw work unit 1, right? So what happened there? Here's what happened there. Right? Remember how CPUs work, right? They have registers. So here's core 0, here's core 1, okay? Here is entry count, out in memory somewhere, okay? Core 0 says, oh, I need to do this operation, right? Oh, I shouldn't say entry count, my bad. I want next entry to do. Right? So next entry to do. And next entry to do, in this case, make sure I did the right one. So is the work unit 1, right? So next entry to do in this case, the value that's stored in this location is 1, right? So here's what happens. Core 0 goes, oh, I gotta go check next entry to do and potentially increment it. So I'm going to load it in here. So now it goes into a register, right? So inside the register of core 0, there's a 1. Core 1 goes, oh, I got to load that in. Let me load that in. So now in the register of core 1, there's a 1. Because remember, processors don't necessarily operate on memory. There are such things as memory ops in x64, but a lot of times what they do is they move something into a register, do a bunch of work with it, and then put it out. So remember, it's a copy. It effectively copied these values, right? These values got copied, they got cloned into the registers of the cores. It then does a test. It says, oh, I don't know, what's entry count? Is this greater? Entry count is maybe 4 at this point or something. Who knows what it is? So it's like, oh, okay, yeah, you know what? I got to increment this. So it increments it, and it makes it a 2, right? Core 1 goes, oh, you know what? I got to do that same thing. It increments that and makes it a 2 as well, right? They then go and they both write out the value, and they overwrite this value with 2, and they both write 2 back onto it. So both of these cores now think, right, that work unit 1 is the one they should do. And they both think that they updated the value to 2, which they did. But what that means is that work unit 1 is actually getting done twice now by each, these cores, each does it, right? And that is bad. If that was rendering, we just lost 1/16 of our performance because we rendered a tile twice. We instead of having 2 different tiles being rendered by 2 different cores, we rendered the same tile on both cores. So does that make sense? Do mutexes that I've seen used for multi-threading code in other places rely on those interlocking instructions, or are they something completely different? Yes, mutexes are actually just operating system primitives that are built off of interlocked primitives in the x64 processor. The x64 processor, I guess I can't think if there's anything else that might be relevant there, but on the whole, the mutexes are usually built off of interlocked instructions on the x64 processor. But there is also another thing called transactional memory, which is coming out in Intel processors now. That's a different way of doing it. It's not really about mutexes in quite the same way. But there are some other new synchronization primitives that do some slightly different things. But at the moment, as far as I know, like mutexes in general are just implemented on top of the interlocking instructions. What is your opinion on lockless queues? So I'll be honest with you, I don't really know what people mean when they say lockless queues a lot of the time. I don't actually know which one they're referring to. Like if someone says a lockless queue, do they mean that they don't use any interlocked instructions at all, right? And if they do mean not using any interlocked instructions at all, then I guess I would say, well, it's interesting probably in some circumstances, which is that if you care about the speed, if you have to queue a ton of things and dequeue a ton of things, then that may be worth it to you, right? That may be something that is valuable, right? But if you don't, then I would question, a locked increment is really not very expensive on an x64 processor. So, if the complexity of that queue at all is more than just than 100 cycles of doing the locked increment or whatever it ends up being, is it really such a good idea? Because a locked increment queue is really easy to implement and pretty hard to mess up. Whereas trying to do it without that seems a little trickier, but I don't know. So I don't have a strong opinion about them. I am not, I do not try to do fancy multi-threaded code usually. I just do standard work queue stuff, and I make sure the work queue elements are pretty big, and I don't have to deal with stuff like, oh my god, what if we have to, make the granularity of this multi-threading be like millions of work units a second or something, or weird stuff like that. So, it doesn't tend to be a thing I think about. What's the point of an infinite loop to begin with? It ends at some point, doesn't it? Well, at some point, not really. I mean, we could very well make this loop be infinite for reals. Because the thread will get killed in exit process. So we may never really care about having it closed down. So yeah, in the case of threading, you really can have literally infinite loops. What threading libraries do you recommend and why? I never use any threading libraries. Locked increment is so easy, I find, that I've always just been able to use locked increment. I shouldn't say just locked increment. Locked compare exchange, locked increment. I just use those. And it's really easy to build a queue with them, so I never use, as far as I'm concerned, using someone else's multi-threading libraries is probably just an invitation to inherit a bunch of crappy bugs that are in there from them. Because I've seen Boost, and I would not trust the people who coded Boost to write single-threaded code for me, let alone multi-threaded code. What's better, a job scheduler from where each thread can get a job, or separate queues for each thread? So basically, it depends on the workload. So taking the render as an example, you might say, well, why would you have a queue at all? Because we know we have X number of threads. Why don't we just have each thread do a specific set of tiles, and that way they don't have to communicate at all, right? And that's a perfectly valid strategy. And we may find that that's a better strategy than what we're doing. I don't know. I kind of want to show the work queue version just for educational purposes because it's more general and applies to more things. But it could be fine to do it that way. But even in the renderer case, it may not be true that that is the right way to thread it. And the reason is because different tiles may take different amounts of time. Okay? So consider the following circumstance, right? And so just to give you just to tie it into your question, right? So you're saying, what's the difference, right, between I have something that looks like this, right? Q, 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 right? And each thread pulls from a different queue. So when I go to distribute my render jobs, I take the screen and I break it up into tiles. Oops. And I break it up into tiles, and I assign each of those tiles to different threads, right? And they each get their own queue. So we like queue up tiles in each of the thread queues or something like this. Or better yet, we do away with this entirely and we just have each thread knows which tiles it does and it just iterates over them, right? What's the difference between that and just having one queue, right? Where each of the tiles piles into it and all of the threads pull out of it, right? And just to give you some nomenclature here, this is typically called single producer, single consumer, right? These are consumers of the queue, and these are producers of the queue. Single producer, single consumer. So basically, like each queue only has one thread writing to it and one thread reading from it. And this is called single producer because it's the same here as here. There's only one thread that's writing the tiles. Multiple consumer. So this is single multiple, right? And you can look those up. Those are standard terms that you can read about. Well, the reason to prefer this method is that what if, say, this tile takes a hell of a long time, right? So this tile takes 100 milliseconds. That'd be too much. This tile takes 10 milliseconds, but the rest of these all take 1, right? Well, what we'd like to have happen, ideally, is we would like to have the rest of the threads be able to do all the other work while whoever unfortunately got stuck with the 10 millisecond tile does that work, right? Because think about what would happen in this queue case. What would happen in this queue case is one thread gets, say, this tile, this tile, this tile, this tile, and this tile, right? And worse yet, let's say that the 10 millisecond tile was actually up here in our worst case, right? So now we've got 1 millisecond, 1 millisecond, 1 millisecond. So let's say this whole row, this whole column of tiles went to this queue. That means that as this thread here, he pulls off the first thing, it takes him 10 milliseconds. He then still has to pull off these other 4, so it's still going to take him another 4 milliseconds, meaning that the total frame time will be 14 milliseconds for this guy. All the rest of these guys only had 1 millisecond tiles, let's say, so they all completed in 5 milliseconds. But it doesn't matter that they all completed in 5 milliseconds because this guy took 14. So that means our total frame time is still going to be on the order of 14 milliseconds. On the other hand, if this had been a general work queue, this guy would have gotten stuck with a 10 millisecond guy, yes. But all the rest of these guys would have been done by other threads by the time he completed, right? So our total frame time drops from 14 milliseconds to 10 milliseconds in the single producer, multiple consumer case. So when you know that you don't have too many work units, like when you have on the order of 100 work units or something, it's usually not worth the extra time savings in terms of enqueuing and dequeuing that you get from going with the single producer, single consumer, because now you don't have to do locked increments or anything, right? Because you always know that there's only one thread reading, so you can actually do a lock-free queue trivially in this case. But if you know that you have a small number of work units, it's almost always better to go with single producer, multiple consumer, because it means that you get this free spreading of the work that you would not have gotten in the case where you've got this queuing happening. Pseudonym 73. I think that the point of lockless is that it doesn't use an operating system level lock. If that's all people mean by lock-free queues, then that's the kind I always use. So I would say I'm in favor of them. But it technically, you can have, like, it's possible to do, so just to make this absolutely explicit, so this is why I say I never know what people mean when they say lock-free, because there's two kinds of lock-free. There's literally completely lock-free, right? There's like, meaning the processor, it's processor lock-free. Okay? And that's actually possible. So for example, in the single producer, single consumer case, you could do a processor lock-free queue. That's totally plausible. All you have to do is make sure that you write to the index variable on one thread after you've done all the writes it needs to do, and you read from that on the other thread. And then you never have to do an interlock, right? So that's actually possible, right? Then there's the other lock-free, which means that no threads ever stall, okay? And that's a very different thing. What that means, that is like cheesy lock-free. All that means is that you're using the processor. It's got processor locks in it, right? So it has processor locks. I don't usually call that lock-free because it still has a processor lock. All it means is that you're not sitting there stalling other threads waiting for another for this process to finish, right? So the kind of thing that we're writing here is actually lock-free by that definition, because it doesn't stall the other threads waiting for one thread to finish dequeuing. All the threads can dequeue simultaneously using the processor locked synchronization primitives. So yeah, this kind of lock-free, pretty difficult, pretty limiting. I don't tend to do it. This kind of lock-free, pretty cheesy use of the term lock-free in my opinion, but this is the kind I normally do, so yes, I am in favor of it. So Fabian says the terminology, the original term was non-blocking, which is more useful for lock-free, and I would like that to be much better, because if that was the terminology, then that makes sense, right? If you called this lock-free and this non-blocking, then now I feel like that makes a lot of sense. But when you start using lock-free for this, it's still doing a lock. Like, that's a lock. It's not... The processor's doing the stall for you in there, so I don't know. But yeah. So both Pseudonym 73 and Fabian said that normally people, when they typically say lock-free, they're actually referring to this case. So yeah, if that's the case that the original questioner was asking about, then that's what I tend to do, actually. Is it reasonable to synchronize the receiving of network packets on one synchronized thread? Sure. I mean, the network card can't produce packets fast enough for an x64 core to choke on them. The x64 processor can read much faster than that. So in order for you to need multiple threads simply to receive network packets, if you were talking about like a low-level thing, sure, it would be fine. Right? Unless you had some kind of amazing network card that was like just crazy out, super fast, and you were sitting right on some kind of fiber link, right? But almost always in network packet receipt case, it's going to be the outbound link, the inbound link rather, that's the slow part, not you dequeuing them. Now, what is not always the case is that the stuff that has to happen with those network packets, like the crappy TCP/IP stack on Windows or something, or what you need to do to actually process each packet, that may be a lot of work, and that may be slower than inbound. And at that point, you need to make sure that you handle them on multiple threads, potentially. But the actual just getting the packets off of the NIC, like you have to be on the world's most amazing internet connection before that is going to outstrip an x64, because the x64 could handle that no problem. Later in the development cycle, will you go over threading for other operating systems like Mac and Linux? So it's yes, but there's really not much to it. It's the same as the Win32 one. You just call like this function that's like start threading, usually on most of them. So it's not that hard. But that won't be for a while, because that's only when we start doing ports. what are the advantages of having a queue of jobs instead of creating a thread every time you add a job? Well, okay, so that is because we are not queuing. We are not queuing for overlap. We are queuing for performance, and it's important to understand what these two different things are. Okay. So I want to talk about these because this is. I'm glad. In fact, I'm really glad you asked that question because we never really came right out and said this. Okay. So what I want to underscore here is there's two totally separate reasons you might want to thread. Okay. One is because you are trying to overlap work. All right. And in that case, let's say that we have 30 things that need to happen, right? One of those things is the UI for our application, okay? And we're not a high performance application. We really don't care. We're Apple or somebody. We don't really care, or you know what, I shouldn't blame Apple. We're Android. We're the people who write Android, so we don't care about the user experience at all if it's laggy or whatever. So we're just running the Java VM and having a UI party and stuff's just going nutsoid, right? But we've got these 30 things that we want to do and we know they're all going to take a second or something, right? A totally valid use of threading is just to kick off 30 threads, let them go do their thing, and then we'll at least know that that UI thread will get some time now and again, and it'll be janktastic, but it'll at least run. So the user will still be able to do some input and it's fine, right? So this is threading for overlapping. The goal here is not performance. The goal is simply to have 30 things that happen simultaneously and not have one of them stall completely while they happen, right? Threading for performance means we are trying to get the maximum number of cycles of work out of this processor as we possibly can. So if this processor, right, if the CPU has 16 cores, or I should say 16 hypercores, because this processor actually has 8 cores, I believe, but they have 2 hyperthreads each or something like this. I don't actually know. Something like that. If the CPU has 16 hypercores, but we create 30 threads because that's how many things we have to do, then what we are essentially doing is we're forcing the operating system to do our job queue for us, right? These 30 threads will all go into the OS scheduler, right? As if they were a job queue. That's what's going to happen. Now, the OS knows absolutely nothing about these threads. It does not know that they should be, that we are trying to have the maximum performance possible. It may think that we're trying to interleave them so that they all get a little bit of time. It could think all sorts of things. It has to save all kinds of register state, right? It has to do interrupts to switch them. There's all this stuff that the OS scheduler has to do. If we, instead, were to create 30 work units on our queue, all we have to do to dequeue them is that interlocked exchange, right? That's 100 cycles or something on that order, depending on the processor, right? I think sometimes it was as much as 300 cycles, so I shouldn't say 100. Something like 300 cycles. But it's never, I don't think it was ever worse than that. Let's put it that way. We know that we can totally beat all of this crazy work the operating system has to do where it has no information. It will switch these out multiple times potentially. It'll do register saving and restoring. It will have to, you know, it's using the schedule interrupt to do those things. All of this stuff that doesn't have to happen, right? We can save all of that work by just doing our own job queue. So because what we care about is performance, we care about saving all of the cycles that would be blown, that would be wasted, and getting it down to just that, at most, you know, something like 300 cycles, that it actually costs us to do this thing, right? And that's really important. And so what I want to underscore there is there really are two things that threading does, and we care almost not at all about this one. There will be once in a while where we do care about this one, and that'll be when we're doing async I/O, which will probably be coming up shortly, actually. Once we got threads in there, we might as well get our I/O asynchronous. So there are times when what we care about is actually the overlapness because we want to wait for like the disk to do things or we want to do other stuff. So there may be other times when there are threads, either the operating systems or our own, that are executing on our behalf where really it's not about performance, it's about overlap. But for the majority of the work that we do, what we care about is threading for performance, which means that we don't want to then go turn around and give a bunch of that performance away because the scheduler, because we're letting the OS do a bunch of work and it doesn't have the information necessary to do the right thing. All right, we all done there? Looks like we're out of questions, and that's good because we're also out of time. Good. I'm glad this is a good stopping point for today too, because it means tomorrow we will basically be able to implement our work queue and start to actually do stuff. Because basically, and hopefully you saw, kind of when I ran this, you could kind of see how these problems that I'm talking about were not theoretical. Like we actually did have exactly the kind of problems that I was saying, where people get the wrong values and stuff gets overwritten and it's not good. So yeah, you saw what kind of happens here. Basically, our job for tomorrow will be to fix that and then just kind of abstract this out into something that we can actually use in the game to distribute our work, at which point we will have multi-threading in the renderer. Now, there is one other problem we'll have in the renderer that has to do with that cache line problem, but we can start talking about that a little bit later. That just gets into memory alignment and the fact that we need to make sure that our loops don't kind of overwrite each other's memory bounds. I didn't want to talk too much about that before because it wasn't applicable in single threading. But now that we're going to introduce multi-threading, we'll see this, or at least we should see it, I think. Again, Intel, one of the things, I know it sounded kind of hand-wavy today when I said it, but this was something that actually, even when I first learned multi-threading, or first, I should say, did multi-threading on x64, this actually surprised some people that I programmed with who had been doing multi-threading much longer than I was, because I actually went and read the x64 manual. x64 is a weird processor multi-threading wise. It actually does synchronization stuff that a lot of other processors just don't do. It's got weird, strong write ordering and stuff like this that's like way better than, let me put it this way. We're gonna be talking about things like memory barriers and this sort of stuff. The x64 actually, for what I've seen, requires the least out of you as a programmer in terms of enforcing the memory ordering and enforcing that stuff happens. So actually, when I say that we're going to have this problem, or that we'll have to work around this problem, what I actually mean is we will theoretically have this problem, and I assume that it will be a problem in x64. But since it's been a long time since I read that, for all I know, maybe the x64 actually just comes in and is like, nope, guess what? Surprise, folks, it's not a problem. So I don't know, but in theory we could have the problem, so I'm going to go over it as well and show you what we would have to do to fix it, because at the very least, for porting's sake, we probably don't want to put ourselves in a situation where we're counting on all kinds of x64 stuff, and then all of a sudden it turns out that people in the community get that big contract from Google to do an Android port of something, and then it's all ruined because Neon doesn't have these or something. I don't know. So point being, I want to show you that either way, and we'll do that. We'll take care of that. So we'll be working on that. Tomorrow we'll get the job queue going, and then the days forward we'll just make sure the render is working kosher, and we'll touch up a few of those things with memory alignment that we want to make sure aren't going to cause any problems, whether or not they do happen to cause a problem on x64. Because like I said, sometimes x64 can save you because it's got stronger memory ordering in certain cases than a lot of other processors do. All right, so I'm going to go ahead and close things down here for the day. Close it up. And also, I think we've gotten most of our Blackboard stuff. We'll have to do one more Blackboard session on read and write barriers. But I think we've gotten most of the blackboarding for multi-threading out too, so that means we should be able to make much faster progress for the rest of the week, because I won't have to spend the bulk of the time drawing stuff. We'll just be able to do it. So that'll be good too. So I hope you'll come back tomorrow and join me for the next step in our multi-threading, which I think will go pretty smoothly, hopefully, but you never know with multi-threading. It's complicated. Yes, please come back tomorrow and join us. It'll be same time, same place, 5 p.m. Pacific Daylight Time tomorrow. In the meantime, if you do want to follow along at home, you can always go to handmadehero.org, and if you order the game, you get the source code all throughout its development. So you can go ahead and check that out. If you want to do the pre-order, you could do that. We also have a Patreon if you want to support our video series. It's always much appreciated. We have a forum site where you can go and ask questions and also get resources like Mac and Linux ports and stuff that the community do, and stuff like this. And finally, there's a tweet bot, which you can check out. It tweets the schedule at you. And we also have this live button, which thanks to some folks who contributed the JavaScript code, Remy and Jakob, again, don't know how to pronounce either of their names, but thanks to them, this now also is pretty accurate. So you can actually check the schedule for the week with the tweet bot and the schedule for the day and stuff like that. But you also, within the window of time when the thing is going to be live, it actually shows a little countdown there, which is pretty cool. So thank you guys for that. It's been pretty sweet. Yeah. So thank you all for joining me. I hope to see you back here tomorrow. Until then, please have a wonderful day, or wonderful programming, I should say. And I will see you back here then. Take it easy, everyone.